Hi all, in this video I'm doing a steam turbine exercise from Power Machines N6. It comes from the August 2011 question paper. It's a very interesting one. So I'll read the statement, analyze the data, and then see how we'll go about drawing a velocity diagram from the given data. So the statement reads, a velocity compounded two-stage impulse turbine has two rows of moving blades separated by a row of fixed blades. That is standard. This is the type of turbines we are dealing with. The inlet and outlet angles of the fixed blades are 36 and 17 degrees. So the fixed blades, sometimes called the stationary blades, are the blades that are in between the two moving blades. Their function is to redirect the direction of the steam. So therefore the inlet angle of the fixed blade gives us beta 1. The outlet angle of the fixed blades gives us alpha 2. So this one is sometimes called the angle of the steam leaving the first row of moving blades or the first stage. This one, alpha 2, is sometimes called the angle of the steam entering the second stage. Okay. The inlet and outlet angles of the first row of moving blades are equal. So these are blade angles at first stage. Both of them are equal. It means another way of saying they are equal is saying there's symmetrical blading in the first row of moving blades. So they are equal, but we don't know their value or their size. The velocity of the gas at inlet of the second stage is 2.2 times the average blade velocity. So here you are given an equation in weights. So then let's analyze it carefully. The velocity of the gas or steam at inlet of the second stage. Inlet of the second stage is V3. So then they are telling us that V3 is equals to something. Then it says 2.2 times the average blade velocity. So average blade velocity is U. So it's 2.2 times multiplied by U, the mean blade velocity. Okay, so we don't have the values, we have the equation. Fine. The mass flow rate is 30 kilograms per second. So that is m dot for calculating power and axial thrust. The inlet and outlet angles of the second row of moving blades are equal. So this one, theta 2 equals phi 2. It also means we have symmetrical blading in the second row of moving blades. There is 4% loss in velocity across all blades due to friction. So now this gives us a K value of 0.96. 4% loss means that you retain 96%. So then 96% in a fraction is 0.96. Okay. So obviously this information is not enough. So, and then we read further on 2.1. It says use a length of 40 millimeter for the average blade velocity and construct a velocity diagram in your answer book. So then here they are giving you the size of U, but the size of U that is given is in millimeters, and we know that whenever we get this case, it means that the scale is not going to be given, and one of the questions would be to find the scale, right? So now this is the information we have so far. And then if maybe you want to just go through this one. So now on this one also they are giving us, they're saying calculate the scale. As I was saying, that the scale is going to be something that they are looking for. They're saying calculate the scale if the relative velocity at inlet to the first stage is 526. So now they are giving us VR1. Relative velocity at inlet of the first stage is VR1 is equals to 526. But then we are going to use this to calculate the scale. This size of VR1, we treat it as an unknown when we do our velocity diagram. So now that is our data. We have beta 1, alpha 2, theta 1 is symmetrical blading in the first stage, symmetrical blading in the second stage. We have an equation of V3 with respect to V2 with respect to the blade speed, and then we have K, and then we are given that U is 40 millimeters. So now you can see now that now that a U is given, it means that we can be able to calculate V3. So in order to get V3, we will take U of 40, we multiply it by 2.2, then we'll get 88 millimeters. So our V3 is a known, is given. So now let's move to the velocity triangles and see whether our information is sufficient, but also see how are we going to then draw our velocity diagram. Okay, so from this information we can then see that we said we were given first beta 1. So beta 1 is that guy. We were then given alpha 2 is that guy. We were then given an equation of calculating V3, and we calculated V3. We were given U, the mean the blade speed, so there is U everywhere. And then we were given equations that theta 1 is the same as phi 1, and then also here that theta 2 is the same as phi 2 for the second stage. Theta 2 is the same as phi 2, right? So now that is the information that we have. Then we will use that information to construct the velocity diagram from start to finish. Once we are done with the velocity diagram, then we will then go on and calculate the scale, right? So now where do we start? We start at the triangle with 3 data points. So if you come here at the inlet of the first stage, we only have U, so there's not enough information yet for us to can start. At the outlet of the first stage, we only have beta 1 and U, that is 2 data points, that's not enough. Then at the inlet of the second stage, we have U, alpha 2 and V3, so that is enough. This is where we look to start, but we just double check. At the outlet of the second stage, we only have one value. So now it means that we now know where to start. Inlet of the second stage, and then we will then move in sequence and complete the other triangles. How do we draw inlet second stage? We are given U. We measure the size of U 40 millimeters. Then we measure the size of alpha 2 17 degrees, and then we draw the size of V3. We calculated it to be 88 millimeters. Then we stop exactly at this corner, and then we join to find V3. We measure the size of VF3. We measure the angle alpha 2, right? Then we will find all the properties of the inlet of the second stage. Then from this one, we go and complete the outlet of the second stage. So far we said we only have U, the mean blade speed. How do we find the other data points? Remember that K is given, so we are going to use K to calculate VR4 from VR3, and then we are going to say flux 2 is the same as theta 2, because we have what is called symmetrical blading. So then when we start drawing the outlet of the second stage, we will have U phi 2 or flux 2 and VR4. Then that's enough to can be able to draw. We will then complete that diagram, and then we move to the first stage. In the first stage, we start at the outlet. When we check at the outlet, we have U, and then we have beta 1. It's not sufficient. Where do we get the third data point? We are going to use V3 to calculate V2. We know that V2 is equals to V3 over K. We are going backwards, so we are reversing. So we divide by K so that we get V2. V2 is bigger than V3, right? So we have 88 millimeters. When we divide, we are going to get a bigger value. So then our data points would be U, beta 1, or inlet angle of the fixed plate, and also V2, discharge velocity of the first stage. Then that's how we draw the outlet of the first stage. Then on the inlet of the first stage, we only have U. Where do we get the other data points? We are going to use VR2 to calculate VR1. We are dividing. VR1 is equals to VR2 over K. We get a bigger value. And then we also know that there is symmetrical blading in the first stage. So whichever angle we have here for phi 1, we are going to use the same angle for theta 1. So then we will have U, theta 1, and VR1. That is 3 data points, and then that is how we will draw this triangle. Then our diagram will be complete like that. So it's always important, make sure you analyze the data, make sure you don't confuse your inlets, outlets, stage 1, stage 2, and the different velocities, VR, VFs, and absolute velocities. You don't confuse your inlet and outlet angles. You don't confuse your angle of the steam versus the angle of the blades. And then also you plan where you are going to start. You check whether the information you have allows you to can be able to complete the other triangles. It's important we do that before we start, because it's easy to start at the wrong place and then only to find out after 30 minutes that you started at the wrong place, and then you have to start afresh. So hope you are having fun, you are enjoying doing the velocity diagram of an impulse turbine in N6. Thank you. I hope you understood.